Hi, good afternoon, everyone. Welcome to the guest lecture series of Advanced Modeling for Building and Community Systems. Today is our great pleasure to welcome Dr. Sen Huang from Oak Ridge National Laboratory to introduce his research in the Connect community for energy resilience. Dr. Sen Huang has been working on modelical modeling for nearly a decade now. He was also the recipient of the IBIPS USA Emerging Contributor and the IBIPS Award, Young Contributor Award. Yeah, so he has been working on advanced modeling for chiller plants, communities, and many other energy systems. Without further ado, let's welcome Dr. Sen Huang.
Good afternoon, everyone. Thank Professor for the kind introduction. So this is actually the third consecutive year for me to give like a presentation at the professor's course. I really consider it as an honor and also really appreciate this opportunity to exchange kind of knowledge with the students who are interested in modelic modeling. So today I'm going to talk about the kinetic community. I'm assuming that some of you may have a question regarding what kinetic community is. To answer that question, I would like to start my presentation with a real-world example about the kinetic community. So as you can see in this figure, we have a kind of picture of a like real like a residential neighborhood in the state of Alabama. So this neighborhood is owned by a local utility company, the Alabama Power Company. So while the kind of purpose to creating this community is really trying to kind of demonstrate the advanced building technology to really see how well they are kind of there is in terms of like a technical readiness for large scale deployment. And to serving the demonstration purpose, I think the community applied very strict energy standard. So with that, they kind of resolving a very high energy efficiency. But besides in the energy efficiency, there are two kind of feature make it considered as a kinetic community. So the first feature is actually the community level Internet of Things network. It's the IoT network. So working with Oak Ridge, we basically create a large scale IoT like a communication network. So basically for each building in this community, we set up a kind of small computing device. So in that device, we install the IoT software so that we are able to communicate this small device with all the appliance in these houses. For example, we are able to utilize the Wi-Fi to talk to the water heater and also using the some like a model bus to communicate with the charger. So through those kind of connection, we are able to remotely receiving the operation data in runtime. For example, the temperature or the power usage for the different device. And at the same time, it also allow us to kind of sending some control signal remotely. So basically, we are able to control the whole like community with a kind of population of the building assets, so that we can, if there's need doing demand response, we're able to kind of sending command through one like a terminal to the whole community. So from this communication perspective, the whole houses are interconnected. In addition, the another feature is that this kind of like a community actually share one microgrid. So you can see the microgrid actually consists of like a large scale like solar panels, and also they have battery as well as a natural gas generator. So that means with this kind of microgrid setting, under certain like a condition, we are able to making the whole community temporarily operate as a island mode. That we can completely disconnect this community with power grid, so that if there is, for example, outage in the power grid, this kind of community can be still self-maintain for a short period of time. So therefore, from energy side, you can see this community is also interconnected. So that meaning that they are able to kind of move energy all around the community without kind of any headaches. So now we have understanding about the basic feature of kinetic community. The question will be why we need that. So there's many reasons, but I would like to focus on two reasons. So the first reason is the cost. So I would like to using the one figure from the recent technical report from Pacific Northwest National Laboratory. So they in this kind of like report, they made a very good connection between the cost and the size. So you can see in this figure, the axis is the kind of installed cost for battery. So the installed cost, including the material cost and also the labor cost to doing all the installation. And then the y-axis is the size. So from this figure, it's become very clear that first, the cost for installing battery is still very high. So you can see the peak value will be almost like 1,000 dollars per kilowatt hour. And then if we consider the general trend, we can easily see that for all the different type of battery and also for all these kind of energy and power range, we can see clearly the cost is kind of decreased when you have a larger size. So why? So that the answer is very simple. It's very basic economics, right? So if you have a large size, the marginal cost for installing additional battery decrease because the fixed or the shared infrastructure for the battery is generally constant if the size of the battery exceeds certain threshold. So that means is from the economic side, it would be more wise to kind of having a larger battery system rather than the small battery system. So that's why we need a whole community rather than single building. And the second benefit is really lie with the like a load profile. So as we know that the energy efficiency or the how effective the energy system work not only depending on the equipment itself, but also depending on the load profile. So basically how the demand change by time. But we know that those load profile is kind of associated with the type of building. So basically different, for example, commercial building, office building, and also the residential building, they have different kind of internal activity. Those will play a very important role to determine how the load change by time. So you can see from the figure showing the right. So if we only consider one type of like a building, like the commercial building, so you can see if we consider the kind of normalized load and also their relationship with the hour index of the whole year, you can see almost half of the time there's actually low load. So that's understandable, right? Because for this commercial building, usually during the daytime or during the very late nighttime, there's no people, so there's no a power usage. But if we combine an additional type of building, for example, if we combine office, now you can see we have more like a fraction of the time where the load is not zero. And then if we do the further added a new building type, then you can see it generally become more and more smooth. So that will be very important because if you have a system that only operates half of the year, so from the operation side, that's really a very bad idea to having the system at all, right? So if you able to combine different type of the building together, then potentially you are promoting the usage of the different device. So that's really very helpful to justify why we need to have a large kind of scale energy system. So if you really consider this problem from the single building perspective, then it's very hard to having a combination of different type of building. So that's understandable. But if you consider community, that's usually more easier to achieve. So that's really another benefit provided by the community. So now we talk about those two kind of like a benefit of like a kinetic community. So we know that there's always kind of like the advantage and disadvantage. So what will be the downside of community? Again, there's also a lot of like kind of challenge we have to overcome. But again, here I want to really emphasize two of them. So the first one is because of the scale. So with a larger scale, we are able to really kind of provide like more like options for doing the system design. But then it's return with a challenge. So what challenge? The challenge is with so many different options, how we are able to make sure we are able to find the best. Because unlike the single system, which is kind of restricted by the size, we do not have a lot of options. For example, generally, it's not kind of wise to having, for example, CHP for a single building. But now CHP for the community is definitely a wider option. But how you are able to consider the so many options, because those kind of different options for the components can be easily propagated to a combination of the options. So it will kind of exponentially expand the searching space, like showing in this figure. So by just changing the different kind of location for the storage, you can see we can easily generate three kind of like equivalent like design. So the question is how you are able to find the best through those almost infinite like options. So that's really one problem. And the second question is really the uncertainty. Here I want to emphasize uncertainty is not like the only the problem only apply to the community. For single building, we also have uncertainty issue. But why it become more like severe at the community level? That's really because the whole community is interconnected. So that means uncertainty in one place can be easily propagated to affect the whole community. So that means we essentially uh, amplified the problem caused by uncertainty. And secondly, because we have those kind of like a large system, then the uncertainty type will be increased. Here I want using the power outage as one example to show the detail about the uncertainty. So the figure here is really showing that from statistical perspective, how the power outage distribute in terms of duration. So from the figure, you can see it's already quite complicated from the statistical perspective. But remember, this is just one aspect about the power outage, because you also have to consider, for example, the uncertainty from the starting time of the outage, and also uncertainty associated with the like a spatial distribution. Because if you consider the whole like a region, you do not have audit for all the places, right? So they also have like a pattern in terms of the spatial distribution. So those one make problem a lot complicated. So how to solve this problem? To solve the first problem associated with the infinited option, one promising solution is using multiple design. So the general idea is very simple. So instead of just using human eyes to check in the design one by one, so we're trying to introducing optimization in the process. So basically, think about the certain space which contains a lot of possible solution. So we are basically trying to map this kind of like solution with the model, so that the model will be coupled with optimization to really find the best solution. So the idea is really simple. But the problem is that right now, the typical process creating model is highly like a manual driven. So basically we have to, I mean, regardless the modeling tool, if you're using any plot, you have the same problem. So because you have to basically converting the design into a validated model. So to supporting this large scale simulation, the manual process definitely is not impossible for the real product test. So that's why we have to consider an option is which is the automation like a model generation process. But do we have that kind of technology already? My answer is we are close, but not yet. So to having a autonomous model generation process require a systematic study. So it's not really just a simple problem that can be solved by one kind of study. So you really have to consider the collaboration between those development for the enabling technology and as well as some application-driven development. So you have to combine the effort together. So basically, it's more like a joint effort for the whole community. So I think in the past decade, there have been a great advance in those enabling technology. For example, a Modelica builds library, which is very good example to showing those advance. To build on top of those enabling technology, Wario has been working on the application side. So right now, we have made quite a few advance, but today I want to using two examples to show the details about those advance. The first one is the chiller plan co-design. So as we know that for the chiller plant system, so there's a bunch of parameter we have to consider in the design process. So I basically categorize them into three groups. So we have so-called configuration parameter. So that means, for example, how many chiller we should have in this system, and also for this kind of water side, do we have primary only system or the primary secondary system? And then the second side, like a category of the parameter is called sizing. So basically for when we have like a chiller one or chiller two, what will be the designed cooling capacity? And also what will be the operation curve for those chiller. And then we also have the control parameter. So once we have multi-chiller plant system, we also need to figure out how we make them operate with kind of predefined control strategy. For example, if we're using 3D machine to determine their a sequence, then we also need to define, okay, what will be the threshold we use to operate the system. So in the past, when we're trying to determine the parameters, we tend to utilize what I call like a nested optimization process. So basically, we have to first determine, for example, the configuration or design, and then we go to this controls, we call it like a control tuning process. So it's still optimization, but it's kind of manual driven because you have to first determine the kind of control, sorry, the design, and then you figure out the design. And then if you want to do more, then you can have another design, and then you want to do another control correspondingly. So that somehow simplify the problem because it's kind of decouple the design and also control. But then when it comes to the larger system, is losing the opportunity to achieving the true optimal. So what we propose to do is called the simultaneous optimization. So basically, instead of just doing this kind of manual decouple, we're trying to co-optimize the design and control together. So that way we can have a much higher chance to achieving a true global optimal. So to supporting this kind of activity, one question is always, as I mentioned, how we are able to make sure the model are able to kind of adjust based on the design. So to achieve that kind of issue, so I basically utilize the module from build library to creating a model template for chiller plant. So basically, I utilize Modelica as the key modeling technology, and then we're trying to make the Modelica model to be a kind of template which can taking the parameter as input. And then, for example, if I determine, for example, the number of the chillers, the model itself will figure out how to mapping the input signal. For example, number of chiller is 2. Then based on that input, they can automatically generating the corresponding composite model for the chiller 1 and chiller 2 based on the user input. So that way, we essentially directly couple the model template with observation algorithm together, so that once algorithm return with a particular design, the model will automatically configure itself to accommodate that design, so that we can work in together. So here are some like a sample result from that kind of co-design process. So the left one basically shows how good this co-design can achieve in terms of the object function we consider. So the x-axis is essentially the supply temperature duration. So basically, we utilize the duration of supply temperature as an indicator about the thermal comfort, because when we design the system, we have to make sure the thermal comfort is somehow met. And then the y-axis is the cost. So basically, we consider both the material cost, labor cost, and also the operation cost. And then we consider two scenarios. One is the co-design. Another is really the kind of some conventional design, basically the sequential based design. So you can see our co-design methods achieve a better result in both sides. So we can reduce in the duration. So that means we can improve the thermal comfort, but also we can reduce in the cost. And then the right figure basically showing some sample output from the operation side. So you can see with the baseline design, you can see this plot basically showing the room temperature. So you can see at the day 119, so we do have some violation of the thermal comfort because the sizing of the chiller is not really providing the adequate cooling. But then for the co-design method, you can see for the two selected days, they provide perfect maintenance of our thermal comfort. So that really kind of justifies really the benefit from this kind of co-design method. And then the second thing we want to show is the auto-tuning PID. So the PID controller, which is the proportional, integral, and derivative controller, is really one kind of feedback control that be used commonly in the like a building operation. So the PID basically utilize the difference between the control variable and the set point as the input, and then they consider three form of the process of this kind of like arrow to determine the control. So basically, they have the P, which is the proportional part. They have integer, which is the I, the integer part, and then the D is for the derivative part. So the P essentially represent the current arrow, and I represent the error in the history. And then the D is a kind of forecast for the error in the future. So depending how we kind of assign the weighting factor for the three different parts, the performance of the result will be quite different. So in the right figure, I basically showing some concept about how the different like weighting factor will affect the performance. So for example, if we made a very small weighting factor for the P part, then you can see the system response generally very slow. But if we make a very high weighting factor, then potentially we are causing some oscillation. So that means for dynamic modeling, the parameter for the PID will be very important. And we actually have one term called PID tuning to describe the process. So when we create a modelic model, having PID controller is somehow inevitable because, as I mentioned, it's kind of commonly used in the real practice. But then the problem for automatic model will be if you have a lot of PID in your model, you cannot really rely on the model itself to figure out the parameter. Then it's kind of causing the trouble because you can making the model generation process totally automatically, but then you still need to go to the model and then tuning all the parameter by one. So that means it basically generally kind of eliminate the possibility to having automatic model when it comes to modelic modeling. So recognizing this problem, we trying to solve the problem by creating a so-called self-tuning PID process. So the idea, again, is very simple. So we're trying to kind of include a relay controller in the control loop. And then based on how the control process respond to the relay kind of signal, then we can try to creating a reduced order model for the process system. And then based on the parameter for this reducer model, we can directly calculating the different weighting factor for the PID. So the idea is very simple. So based on that same idea, we implement a so-called auto-tuning PID components under the OBC library. So I want to mention this is really collaboration between ORL and also LBN. So Dr. Wetter from LBN, he really promoting the idea, like provide this basic concept, how we should make this kind of concept in Modelica. And then I basically provide the implementation according to his concept. And then in the process of developing this model, he provided a lot of guidance to make sure the model really consistent with the business library requirement. This is so far the most complicated model I have created. So I think the trouble is really this kind of PID, auto TID process, including both the continuous and also distributed modeling. So I feel at some point we really reaching some like a limit of the current Modelica environment. So there's a lot of numerical issue we overcome. But good thing that we make this model complete. Yeah, it's a long journey. And then again, this is some sample results. So we basically, to show how it works, we put this PID into a real process. So basically you can see it's a approximation about the typical coil control. So from the interface side, you can see this new PID model is the same as the like a typical like PID. So basically only taking the measurement and the set point and the input, and the output will be the control signal. But for this PID, you are able to provide a kind of like a signal to tell the PID when it should doing the auto tuning process. So in the bottom, we're showing some result. So you can see at the very beginning, we're just using some random PI tuning, PI gain. So you can see it still follow the set point chain, but then there's a lot of oscillation. So that means it kind of confirm our concern regarding the how PID tuning affecting the model output. But then you can see at around 2,200 seconds, we ask the model to do the tuning, and then it's doing some like a relay control response, and then you can see all of a sudden the control signal become much better. So that's really showing that first PID tuning is something we really need to pay attention to. And then it also shows that we are able to make the problem solved with all the tuning process. Okay, so the next part is really about the uncertainty. So I want to, again, showing two case studies to kind of elaborate how we utilize stochastic optimization as a method to like addressing the uncertainty in both design and operation of the building energy system. So the first one is the stochastic optimization for the design. So you can see when we have uncertainty in the multi-dimension, there are two ways to kind of addressing this kind of uncertainty. The first one is we call it the conventional methods. So basically we have to find one particular validation of this uncertainty, consider their probability. So basically we call it the worst validation. So basically usually represent the worst case. And then using this one like a validation of the uncertainty, we utilize so-called safety factor-based design. So the idea is very simple. We're trying to consider those kind of worst case, and then we generate a very conservative result. That's the common practice. And our approach is different. So we're trying to, instead of taking just one validation, we're trying to take a sample of this like a possible like uncertainty validation, and then we put that directly into this optimization, stochastic optimization process. Then we, instead of trying to optimize the design for one particular input, we're trying to optimize the expectation of the output based on the population of the input. So what that means? So that means we will consider two kind of stage in the optimization. So the first stage is very simple. We're just taking, for example, the price and also the limit into the input process, and then we're trying to just minimize the like expectation of the potential cost and operation cost. And then in the second stage, we are consider one particular scenario. So basically, we have one planning stage which consider the stochastic like expectation, And then we have a operation stage which consider multiple potential realization of the uncertainty. So that way, these two can working together to find a design which may not be the best for one particular scenario, but it can make sure we have more chance to having better result, consider the uncertainty from the input. So this is one a simple example showing how we apply the same method to simplify the microgrid. So the fourth figure basically showing the general cost distribution. So basically you can see in order to utilize the microgrid, we have to spend quite a few money to really, for example, installing the battery. And then all the benefits are all from the utility incentive. So basically, we have to see that because we have more device, then it inevitably will increasing the cost in terms of the capital and also the maintenance. But then those costs will be largely offset by the benefit from the utility company. So because you can see from the figure in the below, we are able to kind of utilize those DER like battery and also the diesel like generator to reducing the peak demand. So the utility company actually give incentive to reward that kind of action. So that's why the figure here is really showing that we are able to having a better cost only when there is incentive from utility company. And then most interesting part is really from the resilient part. So you can see, as I mentioned, because we have investment on the equipment, so that's really definitely causing some a decrease about cost, because you can see most of the benefits actually cuts out by the cost. But if we consider the survivability, the results are totally different. So we basically consider the same kind of random select uncertainty input, and then we're trying to calculate how much chance we can survive based on the length of the day. So you can see with the design where there's no DR, so we definitely can reducing cost. But you can see when we have increased the duration of an outage, so the survivability dropped immediately. So basically, we cannot survive most likely for 1 week. But with the DR, although we sacrifice a little bit kind of a cost, but you can see for the whole 2 week duration, we have very high chance to survive. So that's really showing that we actually have some kind of trade-off between the cost and then survivability. So I mentioned that the cost is kind of highly associated with the incentive from the utility company. So we also studied a kind of scientific study to try to understand so how things change if there is change in the incentive. So you can see by just changing, for example, the utility rate by just 10%, so you can see the result are totally different. So we can have a more better a net a cost benefit, but also we have a lot of kind of saving in terms of the general a price configuration. So this is really showing that right now we have a lot of dependence on the utility company in terms of their policy when we're trying to promoting the concept of the connect community, because as I mentioned, from the cost perspective, there's really not a lot of benefit. But we probably also need to consider the benefit on the grid side, because as I mentioned, just from the building or the community side, the cost is generally not that significant. It's very highly dependent on the utility. But if we consider the benefit from grid, potentially we have actually a higher observation happen in a higher level. So basically consider both the grid and also the community together. Okay, that's for the design. And also I also want to show some supply observations for the operation. So to start, I want to provide some background information. So in the building the grid integration, we have a concept called dispatch. So the idea is very simple. So we having some like a input from the like a grid, for example, the electric price, and then based on that kind of price, we can basically doing some optimization to generating some like a dispatch signal. So basically, the dispatch signal meaning that what will be the desired power consumed by the certain building device. And then based on that kind of dispatch signal, we can kind of rely on the supervisor control and also local control to kind of converting those signal into the actual like operation schedule of device. So we call it the kind of dispatch process. For this kind of dispatch process, you can see at the top level, we actually running a, I would call a model predict control. So the concept is, again, very simple. We're trying to minimize the cost, but the whole operation is highly depending on one like a constraint, which is the thermal comfort like constraint. Basically describe what will be the relationship between the power target and also the temperature, because we have to make sure the temperature will not be the thermal comfort will not be sacrificed when we're doing this kind of demand response. So that's why this kind of function is very important. Another approach is really just using like the two stages circuit operation. As I mentioned before, the same concept we have like planning and also operation. So the reason we want to consider this stochastic is because we want to really consider this like a prediction error in the room temperature prediction. So I want to using one simple example to show how the error like looks like when we think about those like room temperature prediction. So let's consider a typical media office building. So you can see it have a three layer, and the whole building is kind of like served by a typical rooftop unit system. So the system we actually modeled with Modelica plus and plus. So basically and plus is handling the envelope, and then we're using Modelica to model the control system. As shown in the figure in the lower right, you can see it's basically showing the basic idea. So we have a like a on-off control for the RTU. And then based on the room temperature, there is a kind of on-off change for this like a system. So to kind of capture this kind of like a room temperature change, we utilize a simple linear model, so which is the commonly used model in the like a real practice. So I think we use that really just because it's a linear model that can be easily handled by most advanced observation like algorithm, and also it's very easy to like a trend, because we can utilize a lot of tool to like identify the parameter for the model using the like data from the real building. So the model is very simple, but then the problem is that the accuracy is also not very good. So you can see in the right, we showing two scenarios of their prediction. So for the first scenario, we're trying to predicting the room temperature every 1 hour. And then in the right side, we're trying to predict the room temperature every 1 minute. So when we do the prediction, we do the so-called auto regression. So basically, we utilize the temperature from the previous the prediction in the previous time step at input to predict the room temperature for the next time step. So that way we will trigger the error accumulation. So when you have error in the one step, it will propagate through the incoming time step. So you can see when we have more like a high resolution of prediction, you can see the error is increasing dramatically. And if we utilize this temperature as input to estimate the power, so you can see very easily the error increase dramatically. So especially when we have like a system operating. So that will causing trouble because you have like a very poor prediction. So that will kind of prevent the observation algorithm to find the optimal value. So this is the one example to show how the prediction inaccuracy affecting the result. So the top level is really the original like like a determinist like a load dispatch. So you can see in the bottom one, basically showing the price like a signal. So you can see at the very known time, we have very high price. So that means the power grid generally expect the building system to reduce the power usage. But then because the poor like temperature prediction, so you can see we actually not respond that dramatically. So you can see there's a little bit kind of power decrease, but not much compared to the price change in the signal change in the price trajectory. And similarly, it generally kind of smooth, doesn't change a lot. So that not because of this action doesn't drop, is really because the prediction is too bad. So it's really affect the operation preference performance to find the best result. But in the contract, when we utilize this kind of stochastic operation, so you can see the different are kind of obvious. So when we have like a very high price, we immediately reducing the power usage. So it's more like responsive to the price change because we consider a stochastic operation. So basically, we implicitly consider those uncertainty in the room temperature prediction into the decision making process. So that really much better improve the control performance. And then we also can see that from the room temperature. So you can see, again, we plot the room temperature set point, which is the like output from the like a power dispatch signal. So you can see when we do the the conventional like determinist like observation. So you can see the temperature set point is for most of case is above the baseline. So that means for most of case, we are actually curtail the usage of the power in the building. So basically, we kind of make people suffering when we're trying to providing demand response. But then if we're using the stochastic audition, so still we have the problem. So most of the time, the room temperature kind of is still above the baseline. But you can see in this case, there's more chance where we have like a room temperature set point lower than the like a baseline. So that means we are not always ask people to suffering. We still kind of make the best use of the price chain to really make sure that the building is it behave like a battery. We can charge and also discharge to make sure the impact on the building operation is generally minimized. Okay, to summarize what I present today, so I think we trying to working on the kinetic community from two different aspects. One is the model-based design, really trying to utilize the autonomous model generation process, so supporting the model-based design so that we can better manage the infinite input from the design option. And then on the uncertainty part, we're trying to promoting the stochastic operation to improve both the design and operation of the community. So in generally, I think right now the we see there is a chance to combine the two as one. So basically, we can really make sure that we can also introduce the stochastic operation into this like model design process. But right now, we are still in the very early stage. So most of the modeling development is really just for supporting the determined operation. So I'm hoping that with the collaboration with like PSU, we are able to exploit like a more like a chance to really combine these two kind of like a research direction together to really help us to promoting the kinetic community, the general like deployment in the real world. With that, I will conclude my presentation. And if you are interested, please check our publication and also the model and also released in the business library. So if you are interested, please check the model document from Airbnb's website. Yes, thank you so much. And I'm ready to taking questions.
Thank you, Sen. Yeah, this is really very interesting, very exciting to see that there's a lot of things ongoing at the national lab side. Okay, is any question from our audience? This is very technical heavy, you know. Okay. Yeah, I do have a question. So yeah, so this is my it's a Modelica class. I see you mentioned a little bit about Modelica, right? So maybe could you please elaborate more how Modelica play important role here, or maybe in other words, right? Why do you select Modelica? Why don't you just use other tool?
Yeah, so that's a very good question. So I think first of all, I think as I mentioned right now, most of the Mathematica related work is really on the model-based design. So we kind of at the very early stage to trying to exploit the usage of Mathematica to supporting the model design process. So for example, the chiller plan model is the template is created by in Mathematica, and also the auto model is also like a implement in Mathematica. I think only through Modelica we are able to having one kind of completed representation of the whole building system. I mean, we have like a different tool available in the market, but they are not really designed to providing a kind of like a kind of one-stop solution to model everything. And only Modelica provide the equation-based modeling like a platform so that we can consider everything, so we can put everything into the model. And then because Modelica is also very like how to say, it's kind of leveraging the most advanced modeling technology. So it's object-oriented. So that's making the template and also the self-configuration feature possible. I think, in my opinion, those kind of feature is still able to achieve with conventional tool like N+, but the effort we need is much higher. And then again, also, I acknowledge that for the stochastic part, right now, Modelica is not that be kind of used like widely in our current work. But I do see there's a lot of chance to really utilize Modelica to further promoting the uncertainty quantification. As I mentioned, Modelica is really the one-stop solution to model everything in one platform. So we are still in the early stage to explore that, but I do see there's a lot of chance. So that's why I utilize the current result as just one kind of like providing some context so that hopefully the student in this course or the audience, if you are interested in this aspect, we can definitely working together to further explore the usage of Modelica in this research direction.
Excellent. Yeah, we have, I think, a very quick question from the audience. Then maybe next one, Huangdi, you can ask a question. First, it's from the chat window. Is the new PID auto tuning component compatible with both the PID controller in the MSL and MBL libraries? MSL is Modelica Standard Library, MBL is Modelica Business Library.
I'm not really sure I follow that question. So the auto tuning PID controller is part of the Modelica base library. And right now it's supporting both PI and also PID controller. So I don't think it have any restriction about the Modelica side, but we do have some restriction about the type of PID controller we support. For example, right now we do not supporting P only control. I'm not sure if I answered that question. Sorry.
Okay. Yeah, I think, yeah, if I understand correctly, anyone who want to use that PID auto tuning component, they have to download the Modelica Business Library together with Modelica Sun Library, right? So because this is part of the Modelica Business Library.
Yes. But I mean, I want to mention this is actually under OBC. So OBC is kind of one self-contained like a sub library within the base library. So that means it doesn't utilize anything outside OBC. So in generally, you should have no problem to use that without utilize like a so basically if you're using a model from like other sub package, it should not affecting this controller.
Mhm. Great. Okay. Yeah. let me, I think Juan Diego, you have question. You can, I just unmuted you.
Yeah. Um, yeah, hi, Dr. Wong. I had a question about the stochastic design because if you're using it says like multiple realizations, therefore you're sampling and running the optimization multiple times, but then we see in the results just one value. So does that mean that you took the results of the optimization and you simulated into just one case scenario, and that's what we see in the results?
Yeah, that's a very good question. So the two-state operation actually, as I mentioned, consider two parts. So we have the planning part, which only consider the expectation. So we are not really consider one like a specific scenario. We're trying to really find the solution that can resolving the highest expectation value for the like a decision variable. And then we do have a bunch of the operation stage modeling or operation stage operation to consider individual like a sampling scenario. So basically, we have if you have like 100 scenario, then we have 100 like operation state operation to supporting that kind of like searching space. And then the two will be kind of communicate in the process of operation so that we can, although we have just one result, but the result is really for the whole like sampling, not really for one particular input.
Thank you.
Yeah, I do have a follow-up question about the PID auto-tuning. Um, so what is numerical performance? Let's say, in a real building, I have hundreds of PID control need to tune, right? So this is, the work you did is amazing. I just wonder, like, can I just put them in all of my PID control in my large system model? Then I don't need to worry about tuning at all.
That's the case. That's the idea. So I think right now we make the model self-contained. So that means you can just drag that into any control loop and then just provide the signal about when the PID tuning should occur. Then it will take care of everything by itself. So I think the one scenario would be, for example, you have a PID that's working during the like occupied period. Then you can ask the PID begin to tuning at the very early morning, and then the good thing that the PID is supporting multiple tuning signals. So that means you can tune like every day. For example, you consider the system declaration. You can tune at the very beginning of each day operation. For example, you can tune the model every like 8 a.m. before the occupant period began.
Wow, that's just amazing. But how about the numerical performance?
So generally there's no iteration involved. So it's a raw-based control. It's very simple. You have the like a signal from the relay, and then the system will automatically approximate the system with a first order model, and then it will generating the output. So in terms of numerical side, it's very heavy, very like a light. But the trouble is that it may potentially introducing some events because the whole process is kind of step by step. Yeah.
Yes. Okay, I see. So basically, you feel so there's not much penalty on the computing speed.
I mean, yeah, as I mentioned, it was introducing the events. So you have a lot of kind of like a PID in a loop doing the tuning, basically introduce a lot of kind of like events in the simulation. So it potentially affecting the numerical side. But in terms of the PI, the numerical solution of the tuning process itself, it really not that heavy.
Okay,
Yeah.
good.
And also, I want to mention this is just so we have a big plan. So I'm not sure whether we can do that with current resource, but we do have a big plan to implement the different type of tuning. So right now, the tuning we are implement is very simple, is raw based. So we do have plan to implement two additional like approach. One is opposition based. So that will be more advanced because it will like not only tuning one PID at one time, it actually can consider multiple PID as a whole. And then we can using operation to find the best combination of the PI like again to this kind of like a loop. And also we also have another plan to utilize instead of like operation, we can also using some like a machine learning method to further improve that. But again, this is really depending on whether we have enough resource to make it happen.
Yeah, wish you guys will receive a resource to develop more useful models for the community.
Yeah, that's also I hope. Yeah, we really hope that this model will improve the or make your life easier when you're creating
Yeah.
like a molecular model.
Okay, I see Huang has a question tapped here. Say, does auto tuning output the optimal coefficients of PID to use in other program?
Yeah, so I think if you want to export those tuned like a PID parameter, that's possible. So you can just having some co-simulation interface.
Okay, nice. Okay, any other question from the audience? Answer?
Sure, I have another
Yeah.
question.
You can just, yeah, you can.
Thank you for the presentation. I have a question about the model template because I noticed you mentioned that we can design the size of the battery based on the model template by optimization. But my question is, can we change not only the size of the battery, can we change the equipment in this system? For example, in some case, I want to use the battery energy storage, but in other case, I want to use the thermal energy storage. Can we just change the equipment?
Yeah, first of all, I think so if you are referring to this study, is not like complete with a model template. So right now we're just using very simple like equation to doing the proof concept. So I mean, so we have like some common equation for battery and also for different DR in this optimization process, but we didn't manage to including Modelica into this process. So basically, I think I understand your question. So basically, having Modelica in the process will provide more like a kind of flexibility or more like a input for the audition. But right now we are not at that stage yet.
Yes, thank you.
Yeah. So the template we develop is for the chiller plan. So for this kind of particular system, we are able to taking the three type of parameter as input to generating the corresponding Modelica model for the chiller plant.
So yeah, just follow up for the chiller plant. So basically, you mean that you are able to do a number of chillers, right? And so are you able to change the control sequence?
Yes. So I think you can, it's not control sequence, it's more like we predefine the control architecture, but
Okay.
then you can like using parameter to adjusting that. For example, if you have two chillers, then the state machine may only have like three states. But if the chiller number increase, then the controller will be automatically adjust its internal like a sequence.
Okay, good. Yeah, so is this sequence like based on like actually guideline 36 or where you get your sequence?
So the sequence is based on the ASHRAE like handbook. So this work is performed like several years ago. So at that time, ASHRAE guideline haven't including the water side into the like a scope. So that's why we
Okay.
didn't got a chance to do that. Yeah.
I see. Okay, good. Okay, any other questions from the audience? You can raise your hand if you feel speak out is easier for you, or you can type the question in the chat window. Okay, if no more, let's close this session. Thank you again, Sen, for the wonderful presentation. It's always, very fun to learn your new progress. Even, this is third lecture, but I think you updated the entire content from last year. Really appreciate the efforts of creating the new information for us.
Yes, thank you so much for the invitation. And also, I want to mention that And the reason I changed this kind of content is really hoping that I can using this content to kind of facilitate the further collaboration with PSU. I know that the developers team is really working very intensely on this aspect. So hopefully we can really have a more collaboration in the future to making things more like interest, I guess.
Thank you. Yeah, definitely we can discuss more on that. Okay, thank you all the audience. So we stop.